Right, so we've been talking about glomerular filtration rates. We've been talking about renal autoregulation. We're going to move forwards. We're going to talk about the juxtaglomerular apparatus. This is just a little bit more in detail look, just a different way to look at the glomerulus that we've been looking at about already. So in terms of the glomerulus, sorry, in class. All right, so we have the corpuscle up here, podocytes, which are acting as our filter, right? So those little interlacing fingers of these podocyte cells are going to be allowing the filtrate, which is actually just the blood plasma, to be seeping through into the renal corpuscle, right? So the efferent arteriole is bringing the fresh blood in that needs to be filtered, and the afferent one is going to be bringing what's left out. The cells that I want you to kind of pay attention to are going to be the proximal convoluted tubule, which is going to be up here at the top. It's actually labeled, so there's this. And then if you look on, let's see, on the left side of the screen, the sympathetic nerve fiber, which is one of the ways that we are controlling blood pressure in the glomerulus, is coming down, and it's putting its little terminals right down here into what we call a granular type cell. Okay, this is going to be one of the ways we're doing it. Another item I want you to take a look at is called the macula densa. Okay, so macula densa is going to be right here. These are going to be some sensory-based cells in the nephron loop. We're going to look at those in a little bit. Those are another way we're going to work on regulation in the glomerulus. All right. Hold on. Gotta turn it. All right. Tubuloglomerular feedback. So this is the flow chart. Here's what we're doing. So if we have high glomerular filtration rate up here at the top, we're going to have increased salt load in the nephron loop. What's going to happen is the macula densa is going to be able to take that information. It's going to say, I got increased salt in here. And it's going to be able to secrete ATP, adenosine triphosphate, which is, you remember, is the energy currency of the cell. This is the cash money that we can pay enzymes to do work. Okay? What's going to happen is mesangial cells are going to be metabolizing this ATP to adenosine. Okay, so it's clopping off that triphosphate. Adenosine is a transmitter. It's going to communicate to other cells. It's going to communicate to the granular cells that we just looked at. And it's going to ask the smooth muscle to constrict. That's going to change the blood pressure, and it's going to slow down the glomerular filtration rate, okay? Just kind of going back. I just want to look here. Granular cells right here, these kind of like blue cells, okay, in the artery. And as you can see, it's an artery, so it's going to have those smooth muscle cells, and that's going to cause that contraction, okay? All right, that's a feedback loop. All right, let's look back a little bit more. Sympathetic control. Sympathetic nerve fibers are going to innervate the renal blood vessels, right? So sympathetic is what? It's going to give us fight or flight type stuff. And it's going to be important because adrenal epinephrine, which is going to wake us up, make us want to, commit to the fight or flight. And its adrenal glands are located on, remember, they're on the superior portion of the kidney. So the adrenal epinephrine is going to constrict the afferent arterioles, and it's going to act like a little bit of a shock. It's going to slow down circulation in there. It means it's going to reduce how much glomerular filtration is happening, and urine output is going to slow down, because the one thing you don't need when you're being chased by a cheetah and you are full of adrenaline is you don't need to stop for a potty break. That could be terminal. Okay? Other things it does is it takes that blood supply of the kidneys, which is really high, as we've been learning, like kidneys really get a lot of it, and it sends it to things that are needed for immediate movement and survival, right? Like muscle, number one, right? Your brain needs to be thinking and making calculations, and your heart needs to be supporting all of it with higher oxygen output to the rest of the body, okay? So it means it can really choke down that glomerular filtration rate, really slow down kidneys, okay? So those are kind of two ways the sympathetic nervous system kind of like slows down, almost turns them down to just a very slow amount of filtration, gets the blood back to the rest of the body, keeps all of that and keeps the water balance back to the body so we can really perfuse those muscle tissues, the brain and the heart with as much blood as possible. Okay, keeps that volume high. All right. We're going to look at the renin-angiotensin system. Okay, renin. It's actually the renin-angiotensin-aldosterone mechanism. So these are hormones. These are hormones that are going to act on blood pressure. Okay. So whenever your blood pressure actually drops, pressure is measured by barometrics. Like you have a barometer outside and it measures, the pressure systems that are coming in terms of weather. Is it going to storm today kind of stuff? Well, the pressure in your cardiovascular system is measured by baroreceptors. So they're little nerve endings that sense the pressure of the circulatory system, right? So they are in the carotid artery, the aorta. So they're up there in the high pressure area. Okay, so that's where they are for the most part. So sympathetic nervous system can trigger the release of renin by the kidneys. And renin's kind of an interesting enzyme. It can be used for kind of a few things. Number one, it can be used in cheese making. So there's that, but that's not what we're looking at. So renin converts angiotensin, tensinogen, right, which is a precursor molecule. So remember, and gen at the end means it's capped. It's an inactive form. So renin comes over, it chops off the gen. Think of it that way. And it activates it into angiotensin 1. Okay. So we've looked at angiotensin, and it has a lot of roles in the body. And the first thing that we noticed about it was it modulated blood pressure, right? The tension, right, of the arteries, for example. Like, were they contracting or relaxing? So that's one of them. But that kind of has a lot of implications throughout the body, and actually can be used to communicate in different ways through other parts of the system. So in this case, angiotensin, we're going to see a drop in our blood pressure. Angiotensinogen, right, the precursor molecule, gets converted by renin that gets secreted by the kidney. And so angiotensin converting enzyme is also going to be released by the lungs, right? We got everybody in here now, right? Angiotensin 2, which is super teeny tiny, now can go and modulate parts of the brain, vasoconstriction in the arteries, and it can also work to start converting aldosterone in the kidneys, which is going to like auto-regulate, okay? Some of the byproducts we're going to see are, number one, we're going to see thirst and drinking, right? Because the blood pressure is low. We're going to say, all right, let's get that volume back up with some water, maybe. Preferably, hopefully that's what you're going for. Vasoconstriction, let's make the distance, or let's make the overall real estate less in the arterial blood supply. So there's just like what we have goes further faster. All right. And then the aldosterone, sorry, I'm choking there. Sodium and water are going to be retained. So we don't lose them through urination. We're going to keep them in the blood supply. We can elevate our blood pressure in these ways. So there's a couple ways to get to where we need to be. All right. So that's what that does. Humans get dehydrated fast. We secrete through our skin, through sweating, so much water. There are some animals that, have you ever seen a cat? How much water they're chugging in a day? Are they like us? Like some of us have these like huge water jugs with us all the time. I don't know about you guys, but my goal is like a gallon a day. If I go to your cat, I'm like, what's your goal for water today? The cat's going to say, lick, lick, lick. And that's it. Humans really go through the water. It's kind of part of our, it's part of our biology. So this is kind of an important system to understand because it happens so rapidly in humans. Like blood pressure drops very quickly. Hypovolemic shock, which means hypo, low volume, blood volume equals shock. Very rapidly in some cases. Okay. All right. Hold on. Let's see if I can turn the slide here. Okay. So lungs, kidneys, converts it. We talked about this. Angiotensin 2 is a really great vasoconstrictor. Your blood pressure is going to go up. Um, it is going to do things, however, like it's going to constrict the afferent arterial. And so that means that we're going to like raise GFR despite having like low blood pressure. It lowers the blood pressure in the peritubular capillaries. Remember that 85% of the cortical nephrons have or are, right? Or 85% of all of our nephrons are the cortical nephrons of the peritubular capillaries. That means we're going to be taking in the salt. Okay. We're going to be taking in the salt. We're going to be taking in the water. Okay. Goodness gracious. So my devices are like giving me trouble. So sorry for, there we go. All right. Adrenal cortex is going to secrete the aldosterone, promoting resorption of any kind of salts, especially sodium, water. In the distal cut of diluted tubule. Remember, that's like the last part before you get to the collecting duct, and then whatever we can get out of the collecting duct at that point, which is like, less, but still there. Stimulates the posterior pituitary to secrete the ADH, which is going to mean that water is going to get resorbed as much as possible through collecting duct. Again, you get thirsty. Okay, so that was the notes on it. So now we're going to look at a couple of other items. We're going to talk about filtrate that's normally resorbed. We're going to look at those percentages. We're going to look at how we get rid of ions, wastes, all of that excess stuff. We're going to compare and contrast resorption in the tubular secretions. And we want to look at the salt and concentration gradients that we have to use in order to do that. We started talking about this a little bit earlier on. We're going to look at the energy you have to use in order to do that. And we'll look at the 3 processes of urine formation and look at the rate of excretion of any solute because it's not immediate. They're all going to do their own thing.